Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 481 Plasma Physics. It is the 14th lecture of this course and the topic is Grad-B drift. First, I will give the learning objective. At the end of this lecture, the student will understand the motion of charged particle in an inhomogeneous magnetic field. Before this lecture, we have discussed the trajectories of charged particle in uniform electric and magnetic field. We are following the book Introduction to Plasma Physics and Controlled Fusion by F.F. Chen and following the third edition. In this lecture, I have taken some of the illustrations from this book. Okay, before we move forward to the Grad-B drift that arises once we introduce inhomogeneity in the magnetic field profile, what we have done in the previous lecture. We have discussed the single particle motion in uniform electric and magnetic field. That is, we have discussed the trajectories of a charged particle when it is placed in a uniform electric field, then in the uniform magnetic field, and then we have discussed the trajectories once electric and magnetic field both are applied in a region where charged particle is moving. So we come to this conclusion that when there is only uniform electric field, the charged particle will accelerate either along the field or opposite to the field line depending upon the polarity of the charge. And when only magnetic field, uniform magnetic field is applied to the charged particle which is moving perpendicular to the magnetic field, so it will move, the gyro motion will be there because of the QV cross B force. And as I told you that we have also discussed the situation where electric and magnetic field both are applied such that the electric field is having a component along the field and also a component perpendicular to that field. That is, once we have cross field, that is E and B are perpendicular to the direction of motion of the charged particle. So then along with these accelerated and gyro motion, there will be a guiding center drift which is known as the E cross B drift. On that will be felt by the charged particle once it is moving in the plane perpendicular to the direction of magnetic field. So how we have obtained this conclusion? We have solved the equation of motion for that single charged particle, and there we have discussed the situation once B is 0, so there will be only a force QE so that it will be accelerated. And also we have discussed the situation when only B field is there, that is E0, so that it will experience a QV cross B force, and that will give rise to the gyro motion. And also we have discussed the E and B field applied simultaneously such that E is perpendicular to B, and also there is a component of electric field along this magnetic field so that the charged particle will move in a helical path. So we have discussed these trajectories, that is the X and the Y. Let's say the magnetic field is applied along the Z axis and there is no electric field, so then we have managed to find out these equations that will give rise to these gyro motions. And as I told you, once there is a finite velocity of the charged particle along Z, that is along the B direction, so along with the gyro motion, it will also move along the field line, so that the net result will be a helical path. And due to the situation when E and B both are applied, so that it will experience the E cross B drift. And we have also discussed in the previous lecture, that is the E cross B over B square, that will be a drifting guiding center because of these two fields. And along with these E cross B drift, we have discussed the various situations, that is we can change the E field by any other force, general force applied with the magnetic field, such that there is a component perpendicular to B, so that we have written the guiding center drift for a general force. That is, this can be QE for electric field situation, so that there will be a drift which is independent of Q. And also we have discussed the situation where instead of the electric force, if there is a gravitational force, so that the drift takes this form. Now this drift depends upon the mass, and also it depends upon the polarity of the charge. So we have discussed these things previously, that is we have managed to clarify the picture of the guiding center motion, and we have discussed these situation on the basis of these diagrams, such that this is the situation where uniform magnetic field is applied, for example in this picture out of the page. So when a charged particle is moving perpendicular to these field lines, so it will start a gyro motion experiencing a force. Now this V perpendicular is important. This is the Larmor radius, and this is for the charge which is let's say one is for the electron and the other is for the ions. And this is the guiding center motion in uniform magnetic field. So if there is a finite parallel velocity, that can be due to the component of the electric field parallel to the magnetic field, or it may be due to the oblique direction of the charged particle while entering in a region where magnetic field is there. And we have discussed the E cross B drift, that is where electric field is applied cross to the magnetic field, and these are the the stretching which is which give rise to these helical orbits. It can be due to the acceleration provided by the electric field, if there is a component of electric field parallel to the magnetic field, while this gyro motion is because of the QV cross B force. Now you can see the sense of rotation for the electrons and for the ion, and one can see that both are moving in the same direction since the E cross B drift is independent of the charge polarity. So with this, now we move forward to the grade B drift, that is having this idea of the guiding center motion when there is electric and magnetic field applied, both are uniform, still there is a drifting guiding center. So now once we introduce inhomogeneity in the, for example, in the magnetic field profile, since uniform field provide poor description for many phenomena such as the planetary field, coronal loops in the sun, tokamak, which have spatially and temporally varying fields. That is, we have to introduce this inhomogeneity one by one at a time, just to see the impact of the inhomogeneity which give rise to guiding center drifts, and that is our aim to discuss in this lecture. So as I told you, in general, introducing inhomogeneity is too complicated to obtain the exact solution for the guiding center drift. So we'll be introducing it one by one, and we'll be trying to find out the approximate solution for the trajectories instead of solving the exact solutions. So for the approximate solution, we need to adopt the orbit theory with the approximation that within one Larmor radius, the B field approximately uniform, that is typically length scale L over which B varies, L should be greater than the Larmor radius. So for example, while discussing the Grad-B drift, we have pictured that situation here. For example, the magnetic field is applied along z-axis, but the field lines is having gradients along the y direction. So again, we are assuming that the field lines are straight, uniform, but there is gradient as the charged particle will move up, that is along the y, so it will experience a stronger field compared to it is moving down. So these are the sense of rotation for the electron and ion. So we'll be saying that the scale over which the magnetic field line varies is somehow greater compared to the dimension of these gyro radius, so that to find out the approximate results. Now these are our expectation, that is the gradient in B, that is the from the figure it is clear that as we moving up along the y-axis, the density of the field line increases, so that this gradient in the magnitude of B causes the Larmor radius, that is the Larmor radius were discussed previously, that is it is due to that force QV cross B, be larger at the bottom of the orbit than at the top, because Larmor radius is inversely proportional to the strength of the magnetic field. So once the strength is increasing, Larmor radius will decrease. So when the charged particle is moving in one gyro orbit, so as it is moving up along that y coordinate, since when the magnetic field is applied along z, so the charged particle will be orbiting that field line, and it will move in the xy plane. So as it is moving along that x direction, so it will experience more stronger field, so that the gyro radius will be smaller, and in that orbit when it is moving away from the y coordinate, that is, so that it will experience a lesser field, so that the gyro orbit will increase, which leads to a drift, as we have discussed previously. Now this drift should be perpendicular to the Grad-B, and also it is B, as previously we know that the direction of the force V cross B, but in this case the magnitude of B is not constant. The magnetic field is still along z-axis. Now ions and electron drift in the opposite direction. These are the situations which we will see on the coming slide through the mathematics. So for that, we consider a charged particle having mass m and charge q moving with the velocity v in a region where I think this is there is a typo mistake. So when a charged particle is moving with the velocity v in a region where there is a magnetic field applied such that it will experience a force q v cross b, the charged particle is having perpendicular component, and also it is having a finite velocity along the field line, that is it is moving in a space where magnetic field is applied along z, having gradients in the y direction, and the magnetic field, as I told you, is applied along the z-axis having unit vector k. So like in our previous lecture, we have to decompose this equation by solving the V cross B in this equation, so that we have the force component along x, y, and z. And it is clear that the z component Z component of force is 0, that is the motion of the charged particle parallel to the magnetic field, that is along Z, is unaffected by the force V cross B. And these are the two components which we have discussed previously. These are coupled equation. We have managed to find out those trajectories for the charged particle in uniform fields. So before we move forward to the inhomogeneous situation, let first have a look at the net force per cycle experienced by the charged particle and having no gradients. That is, for the time being, assume that there is no gradient. The field line, the density of the field lines is uniform, so that the particle will move in a helical object, as we have discussed in the previous lecture in the E cross B drift situation, where x is given by this expression, y is this, and z is having the constant velocity and the position is linearly changing with time relative to some fixed z naught. And these are the component of the velocity for the charged particle for situation where B field is uniform. Now, if we want to find out the average force per gyration along x for uniform B field, so that this QV and Vy is given by this expression, so we just need to put that Vy from here that we have discussed in the previous lectures, so that we need to find out the average value. So this is constant, this is also constant, this V perv is constant, so this is the periodic function sine, and for that we need to consult this handy conversion. That is, if we are interested to find out the average value of sine x, so we need to evaluate it like this, and this comes out to be 0 per cycle. The sine x goes to 0. And similarly for the component of the force along the y, on the previous slide I told you that this is minus qb times vx, and this b is uniform, and this is vx given, we have taken it from the previous lecture, so that the average can also be work out in the same way using this formula. The cos x average goes to 0 as well. Now so once the B field is uniform, the net force along x and y is 0. That is, the charged particle is moving in a helical path, and such that the configurations of the guiding center is x naught and y naught. So now consider that the magnetic field is applied along the z coordinate, but it depends upon the y, as we have discussed on the previous slide, that it is having a gradient along the y coordinate. So that the same QV cross B force is there. For the simplicity, this E is equal to 0. That is, this region is having only uniform, inhomogeneous magnetic field is there. That is, the field line possesses gradient along the y coordinate, and we know that when E is there, so that will give rise to E cross B drift, which we have already discussed, but there will be a correction now because the B field is inhomogeneous. So we are not interested in the E cross B drift anymore, since we have developed that picture of the guiding center drift, but rather we are interested in the effect of the inhomogeneity in the B field, so that what will be the effect once the B field is inhomogeneous, so that the guiding center will now drift because of that gradient in the B field, and under that orbit theory that we have discussed. So for that we need to decompose this form again, as we have discussed. The magnetic field is along Z, and there is no electric field, so that this V cross B can be solved out, having V is equal to Vx I plus Vy Jn plus Vz k, so that we have this the component of the force along the respective axes. So if now we calculate the average force per cycle by having this B field is having gradient along y, so now there will be a force, net force experienced by the charged particle as it moves up during one complete gyro orbit. So as I told you that we need to approximate that situation for calculating the orbits, that is the gradient is along the y direction in a field which is applied along z, that is approximately equal to bz over L, that is that length associated with the gradient, and this should be small compared to this r, that is r is smaller than L if we just rearrange this equation in a way that the gradient length scale is somehow greater than the Larmor radius, so that we are approximate that orbit to be a gyro orbit, so that this can be simplified to this version. Now this means that the magnetic field strength can be expanded in a Taylor expansion for distances y smaller than the Larmor radius. So for that we need to expand the profile of the magnetic field, which depends upon y in a way that it is y naught plus, if you remember, this is y for the gyro orbit we have calculated equal to RL cos of omega Ct plus phi plus y naught. So in that way we can replace the y profile based on the gyro motion. So this magnetic field can be expanded using the Taylor series such that this is the profile of the B field, and that is varying along the y direction. So we have just to keep the first order corrections to that B field. Now if we put the y from the above equation and solve this magnetic field using the Taylor series, we'll be having this B naught plus y times b over curly y, since this gradient is there. So once there is no gradient, so this will goes to 0 and the B field will be equal to B naught, as we have discussed in the situation where there was no inhomogeneity and there was no Grad-B drift. So now we compute the average of the components of the force when the said inhomogeneity is introduced. That is, now we are interested to find out the average force per cycle along x and the average force per cycle along the y coordinate once this B field is given by this expression, that is this B field is not homogeneous and this is somehow varying along the y direction. So in this way the average force along y will no more be 0, but it still goes to 0 along x. So for that we need to find out the average force per cycle along x, so that this is equal to q b vy, so that we need to put the value of B, which is given with the help of that Taylor expansion, and that Vy is also given from the previous few slides. So that if we rearrange this in a way, that is we need to average out this thing minus this thing, that is we need to multiply both the terms, and then this is the situation. This B naught is fixed, the value of q, and then V perp, and then we have the sign, so that the sign x, as we have seen on the previous slide, per cycle it will go to 0, and here this q Larmor radius V perp curly b over curly y, and then again we have sine and cos, since the average value of sine x and cos x both goes to 0 over one cycle, so that it will give us zero net result. That is, once the magnetic field is having gradient along the y coordinate, still the average force per cycle along the x-axis will be 0. However, the average force per gyration is given by minus qb vx, and then we need to put the value of b using that Taylor expansion, and then vx from the previous slide, so that we need to rearrange in the same way as we have done here, so that now the first term goes to 0 because this contains cos x. So we know that the value of cos x goes to 0, the average value of cos x per cycle goes to 0, but cos square x goes to 1 over 2, using that handy conversion, or using those formulas for the average values as I have shown on the previous slide. So this cos square x will be 1 over 2, so that one can obtain a non-zero value of a force along the y coordinate once the B field is homogeneous. Again, one can see that this average force per cycle is proportional to the rate of change of B along that y coordinate. Once this is uniform, this will go to 0 again as in the previous case, and also once there is no gradient along x, so this is 0 still, and this is proportional to that rate of change. Of course, this is proportional to q, Larmor radius, and v perb as well. So that if we put that force which is non-zero for the case once there is gradient along the y coordinate, so it will give rise to a guiding center drift, and we need to use that general formula for the guiding center drift, that is f cross b over 1 over q times f cross b over b square. Now the force is along the y coordinate, since this f of y is not 0, so that there is j, and the magnetic field is applied along the z-axis, so that if we just find out this cross product, so that the guiding center will drift in the x direction. That is, if there is a force on the guiding center along y, so the guiding center will drift because of that force which is cross to B field. Now we can write this, we can find out the magnitude of the guiding center drift for this situation that we have discussed based on the geometry we have shown, and generally we can write in the 3D form for any geometry, that is, this will be equal to half Larmor radius v per b cross del b over b square, where this is the gradient. In our situation, this del b was curly b by curly y. So you can take any direction of the gradient, and you can take any direction for the applied B field. In our case, it was the z-axis, so that the drift was along the x-axis. So you can find out the drifting of the charged particle once the field is inhomogeneous, and that will be grade B drift, since this is proportional to the rate of change of B. In our situation, it was along y-axis. This 1 over 2 comes out from this averaging cos square function appeared over here, and this plus minus of course shows for the polarity of the charged particle, so that one can find out that this grade B drift depends upon the Larmor radius, the v perb, the rate of change. So these are the previous results. One can conclude that positive charge particle drift in the minus x direction, and negative charge particle drift in the positive x direction, as it is clear from this plus minus sign. This grade B drift is in opposite direction for the electron and ions, and causes a current transfers to B. As I told you, once the charged particles are moving in the opposite direction, so that it will give rise to a current which is transfers to B. Now we have shown the situation of the of a region where a B field is inhomogeneous such that it is applied along z-axis, and it is having a gradient along y, so that when the charged particle is moving along that y direction, so it will experience a force along y, so that give rise to drifting of the charged particle. Now we can see that the ions are moving along the negative x-axis, and the electrons are moving towards the positive x-axis, as it is given by these plus minus signs. Again, the Larmor radius effects is clear from these big and small circles. That is, the electrons are lighter particles, so the Larmor radiuses are small compared to the Larmor radius for the ions. So consider the Larmor radius mv over qb. The local gyro radius is large where B field is small, as I told you, and is small where B field is large, which give rise to a drift, as I told you on the first slide, that what are our expectation, because of the gradient in the magnetic field strength, the Larmor radius will be having a local change, and that give rise to a drift. So with this, I thank you for your time.